Welcome to Lecture 7.5, where I demonstrate using the producer-consumer model how to use Mutex, or the pthreads Mutex. Let's get started. So, I have gone ahead and created a directory here. It has a make file and a source code file. The make file is fairly simple. All it has is simply the build line for pthreads. It also has a clean so that I can clean it as necessary. The real key here is the producer consumer source code file. Now, it's missing the actual thread bodies. So that's the first thing we should understand here. We're creating a multi-threaded application, but I haven't added the thread bodies yet. The rest of it's here. I've got two structures. I've got a producer data structure, which takes pointers to a file, takes pointer to an integer count, and takes a pointer to an integer buffer. And a consumer data, which takes a pointer to an integer count and a pointer to an integer buffer. The main function is fairly straightforward. I create the count variable and the buffer variable, and also the two structures. I also create two thread handles. I open a file if necessary, otherwise I use standard in. And then I assign the count and the buffer to the structures so that they can be used within the thread. I then create two threads, passing in those structures, and then join those two threads. So, what needs to be done here is we need to fill in these thread functions. Now, understand that the producer-consumer model, the purpose is to have a producer add items to a buffer, and then have the consumer remove items from that buffer. So our producer is going to have the structure for the producer data. It is then also, I'm going to also go ahead and get the count variable out of that, move the pointer to the count variable out of that so I can use it, and the pointer to the buffer. And so now I can go ahead and use those local variables rather than constantly referring to the structure. So for the producer, I'm going to continue to read, and let's go ahead and get the file pointer out as well. I'm just going to read as long as fscanf is getting a number out. And let's just do a very simple multi-threaded program. The producer will read numbers and the consumer will print numbers. So let's go ahead and declare an integer variable so we can store those values in there. And we're going to use our file pointer to read an integer into the variable n. And as long as fscanf keeps reading a value or getting a 1 back, we're going to continue looping. And when we're done, we'll return from our thread with a null. We don't need to return anything back to the parent thread. Now, we've created this loop. Now we need to insert the data into our particular buffer. I'm going to create an index variable, an integer index. I'm going to initialize it to 0. So that what I can do is just simply say buffer sub I is equal to n. That puts the value into the buffer. And then I go ahead and increment my I. I'm going to make this a circular buffer, so I add 1 to I, but then I take the modulus of max buffer size. And that's all fine and dandy, but who's to stop this? What's to make sure that I don't overflow this buffer? Well, that's where the count variable comes in. Count will keep track of how many elements are in the buffer. So if I have if the count is the same number as max buffer size, I know that I cannot add a new item. So while count is equal to max buffer size, I'm going to go ahead and loop forever. But once I've pulled an item out of that, I'm going to go ahead and add one to count. And what this will do is it will increase, if this is the only loop that runs, I will add items to the buffer till the buffer is full. At which point, line 25 here will just simply loop forever until somewhere else in this system there is a thread that is removing items. Now there is one more thing I need to do. Whenever I have finished reading numbers, I need to add one more value. This is a check value, basically saying, oh, you know, I don't have any more items, so I'm going to send a 0. This, of course, doesn't work if the number list has a 0 in it, but for my case, 0 will work fine. If I did have a 0, I would have to have another way of causing this to stop. Probably not assigning a value, maybe a separate variable that is in my structure that allows me to say, yes, there are more items, or no, there are no more items. I, of course, want to increment count. This notifies any other threads that there is one more item in that buffer. So that's my producer. So my producer loops, reading each value. Whenever it then loops, idle loops until the buffer has a space for this item, puts the item in the buffer, increments the count, increments the index, and goes back up to the top of the loop. So let's look at the consumer. The consumer is going to take items from the buffer. So let's go ahead. We're going to first get our structure, pointer to consumer data. Don't need to cast it because C implicitly casts. We're going to get our count out of there, and we're going to get our buffer out of our structure. They're pointers, and so just as long as we have a pointer, we have actual access to that particular data. This is also going to have an index variable, and we're going to declare a variable as a storage variable as well. In our case, we're just going to loop forever. The for without any test or initialization or increment will never stop looping. It will always be true. So what do we need to do in here? Well, we need to get the item out of the buffer and then increment our I. And so that's the basic of what we need to do, but we also need to take care of whether there's a value in here. And if we find that count is equal to 0, we want to loop forever. If there's nothing in the buffer, then why try to pull something out? Of course, we want to decrement the buffer once we remove the item and then increment our loop. And then let's go ahead and print our data variable. In fact, I'm going to do a match here. Let's go ahead and do a C is equal to 0. C is going to be a counter. And we're going to just simply increment C. And then we'll print out the number that we captured, the number value that we're printing, C, and then the number we got out of the buffer, N. Now, we do have one issue here. What happens whenever the stop value of 0 here, is reached? Well, we probably want to break. So if N is equal to 0, then we'll break, exit out of the loop. And of course, our thread will return nothing. So let's see if I made any errors. I need to learn how to spell PPD. There we go. Fix that. Build it. and it builds successfully. So one more time, we have a producer thread that is reading items from a file, adding those items to the file, but only after it verifies that there's space, incrementing count, and then incrementing its index variable. When it's done reading, it adds a 0, but only after it makes sure that there's space in there, and increments count for the other threads. Over here we have our consumer thread. It goes ahead and loops forever. We'll wait until a value shows up, add that value to this n variable, or move the value from the buffer into my storage variable, decrement our count, break if that n is 0. Otherwise, it's going to increment the index, increment our count, and print out our results. So let's see what we get. So simple test initially. Now I'm going to use echo. Echo has this bash I should say, has this really nifty tool where if within brackets I put two numbers separated by two dots, it will actually do a range of numbers. So I can do something like echo and send it to my producer consumer. And as you can see here, the producer read each one of those numbers and the consumer printed them out. And it seems to work fairly well. If I go up to 100 numbers, it seems to work fairly well. If I go up to 500 numbers, not so bad. If I go up to 5,000 numbers, we're doing good. Let's go to 50,000. Still working pretty well. Let's go to 500,000. This is going to take some time. But after it prints out 500,000 numbers, those two values should match. So here we are, and so far so good. So I'm going to actually do, I've done 500,000, I'm going to do 5 million. This time I'm going to run the tail program, so I only get the last 10 values. So let's see what this does. Now, notice that it doesn't seem to be ending. Let's go ahead and break this. Try it again. Let's see if we can get a successful run at all. And still giving us fits. So we'll run it again. So far, not so good. Up, here we go. But do note that where with 500,000, those last two numbers matched. Here, we have 500,000, but it has an index value that is much, much different than what it was. So we have two issues here. One, it's locking up on us, and two, we somehow get out of sync here. Well, I'm briefly going to show how to debug a thread. So let's go ahead and run our producer consumer program. Now I'm going to run it, but I'm going to pipe to it that echo with 1 through 5 million. Now notice this less than parenthesis. This will actually run this command and put it into a temporary file and send it to the program. We're going to send all that output to dev null because we really don't want to see it, and we run it. So note that it created two threads, and soon enough here it should show that two threads exit. But we have an issue where only one of the threads exited. We did not get an exit on two threads. At this point, we can debug our threads. So I'm going to break by pressing Control-C. Now it tells me that thread 1 received an interrupt signal. That's the Control-C. And this is in, if we take a look at the backtrace, or BT, it shows that it's in the main function where it called pthread join at line 81. So I'm not interested in the main function where it's simply waiting for a thread to end. That's not interesting to me. What I really want to understand is what threads. So if I type the command info threads, It shows me what threads exist within my particular program. I have thread 1, which is the one that's currently active. That asterisk indicates that it's the active thread, and it's the main function, as we saw. I want to take a look at thread 3. So I'm going to go ahead and take a look at thread 3 by typing thread 3. And it tells me I am in the consumer thread. So here's the consumer thread function. I can see in the backtrace that start thread called my consumer thread function. And it's currently waiting for count to change. If I go ahead and print the dereferenced count, you'll notice it's 0. Well, we definitely have a problem here because the producer needs to increment that count so that the consumer can go and look at whatever value it needs to look at. In fact, if we take a look at our index and then take a look at buffer at my index, you'll see that it's still waiting to print out that value. In fact, let's go ahead and do, you can see it would have done 5,000, but there's no 0 here. We probably have to go back to buffer 0. Let's go back to buffer 0. And yeah, you can see here, there's the 0 termination value that should get read after everything's done, but for some reason, count is wrong. What this demonstrates to us is the problem with our program. Our program has a critical section. That critical section is this count variable. Every place we increment or we decrement, such as in the consumer, every place we increment or decrement the count variable is a critical section. Now, you might wonder, is where we're reading a critical section, and it can be considered that, but in this case, our program is simple enough that it's not a problem. Somehow, we need to surround our critical section with an entry and an exit. We're going to do this by using what are called mutexes. So if we create what is called a pthread mutex t, and I'm going to call this mu, and I'm going to assign it a default value. So this mutex will be able to lock our critical section, and then once we're done in the critical section, we can use the unlock method. Now, we of course need to put this mutex where the threads can access it. Right now it's a local variable for main, but we know that we can create pointers that will reference local variables from our main function. So pthread mutex t, we'll call this mu, and it has to be a pointer. We'll do the same thing with our consumer data. We'll put in a mu variable for our consumer data structure. Now what we can do is, during the initialization of our structures, I can go mu is equal to a reference to mu, and we can do the same thing here with the consumer data structure. So both the producer and the consumer have a mutex mu that they can work with. This mutex is actually allocated on the main thread stack, but child thread can access parent thread data. So let's go ahead and move our mutex variable ppd, we need a pointer to mu, is equal to ppd mu. And we'll do the same thing for the consumer. Consumer will also have this mutex. Now this mutex is part of the pthreads library and is actually controlled by the operating system. Any action that's done with this mutex is done atomically within the operating system. So every place we access or every place we write to count, we want to first perform pthread mutex lock on our pointer to a mutex. And then we want to do the same thing. We want to, after we're done, perform an unlock. Same thing down here. Oh, we actually have this where we're setting our termination value, our 0. So we perform the lock and we perform the unlock. And we'll go ahead and do this around the consumer where it's performing the decrement. So at this point, we have a mutex that's created in the main thread and passed to both producer and consumer child threads. The producer locks every increment and then unlocks after the increment is done, and the consumer locks after, before every decrement, and then unlocks after the decrement is complete. Those are the only protections we need here because count is our only critical section. Understand that our buffer is not a critical section. If this program works properly, the index variable that's used for the consumer will always be different than the index variable for the producer, and vice versa. This is simply because, let's say, for example, count is 0, meaning that the buffer is full. Well, at that point, both index variables are the same, but we're not allowed to access that in the consumer until count changes to 1. And when count changes to 1, the index variable for the producer will be different than the index variable in the consumer. So this access to buffer with the I index variable will never conflict with the producer and consumer. Count is our only critical section at this point. So we've gone ahead and made sure that this, we're getting a problem, probably because we didn't put the right structure name there. We build it one more time, and it builds successfully. So I'm going to quit, and let's try our producer-consumer again. Now this is going to take a little bit longer than it did before, but I can say with near absolute certainty that we will get the correct result every single time. A, it will not give us imbalanced values between the count and the number that we retrieved, and B, it should never lock up on us because the count is protected and there are no race conditions with that count variable. So there we see that it ran 3 times successfully. So if we take one more look at this, in our particular case, we used a pthread mutex. The pthread mutex T is the type. Here in my structures, I have a pointer to a mutex, and that pointer is being assigned by the main thread before I create the children thread. And it's being created from this stack variable, this local variable, to the main, which is a pthread mutex T. Inside my threads, I perform a pthread mutex lock before I go into the critical section, and then perform a pthread mutex unlock when I'm done. As well down here, I perform a pthread mutex lock, decrement, and then perform a pthread mutex unlock. And this is sufficient for protecting our critical section within our threads. This brings us to the end of lecture 7.5, where I demonstrate how to use mutex in pthreads.